So now that you hopefully feel a little more comfortable with the process that we've been doing over the last week, finding the real zeros of a polynomial function, we're going to take it a little bit of a step further. So it's not going to be a whole lot newer. It's not going to be a new process. We're just going to take it a little bit farther and factor it over the complex numbers and find the complex zeros as well. So where before we stopped, when we would get an imaginary number, now we're going to keep going and find the imaginary and complex solutions as well. So now when we say the complex zeros, when we say complex, that includes all imaginary and real numbers. So we want to find the complex zero, which is any imaginary zero and any real zero. So we'll start by reviewing the fundamental theorem of algebra. So if f of x is a polynomial of degree n greater than 0, then f has exactly n linear factors and therefore n zeros in the complex plane a plus bi. Okay? So let's go through that again. If f of x is a polynomial of degree n greater than 0, so that just means we're talking about any polynomial that has a degree higher than 0. Okay, so it's first degree polynomial, second degree polynomial, third degree polynomial, all the way up. Then this polynomial will have exactly n linear factors and therefore n zeros. That's just it. When you factor it, linear factors means we are going to factor it all the way so that when you write it in factored form, all of those parts are linear. The degree is 1 for all of the factors. And then that means they have n zeros in the complex plane. So you should have as many zeros and as many factors as there are the degree in the polynomial. So for example, if I had f of x equals x to the 4th plus 3x cubed minus 19x squared plus 27x minus 252, this polynomial has a degree of 4, which means when I factor it, there's going to be 4 linear factors, and that means I'm going to have 4 complex zeros, whether they're real or imaginary. This polynomial has a degree of 3, so we should get 3 zeros and 3 linear factors. This polynomial has a degree of 6, so we should have 6 linear factors and 6 zeros. So this is just a way, this fundamental theorem of algebra is a way for you to know if you've gone as far as you should. Okay? You're not done until you have as many factors and as many zeros as the degree of the polynomial you started with. All right, so let's find the complex zeros of the polynomial function and write as a product of linear factors. So I would like you to write down these directions, at least for the first one. The directions will be the same for all of them. So write down these directions right now. Because remember, it's different than the directions that we had when we did this in class the other day. Because now we're finding the complex zeros, so that tells you that you can have imaginary zeros. And we're writing as a product of linear factors. So we need to get it down all the way for each factor to have a degree of 1. So when it's in factored form, all factors should have a degree of 1. So we're not going to leave any x squareds plus 4s or anything like that. Factoring it all the way down. Okay, so first thing, so we have f of x equals x to the 4th plus 13x squared plus 36. So first thing we always do is check to see if it's factorable. Now, this one does not have 4 terms, so it's not factorable by grouping. However, there is something we can do so that we don't have to do all of our P's and Q's and start synthetic division. Sorry about the bells, guys. All right, so we don't need to do synthetic division on this one because there is a way to factor. So think about it for a second and see if you can remember what we've done in the past when we've had polynomials that look like this. My hint that I usually give is that this is very similar to a quadratic, but it's not quite a quadratic. But it resembles it, it looks just like it. So remember, we can use substitution. Let's let a equal x squared. So I'm going to substitute my x squared in for any x's, substitute a in for any x squareds. So my polynomial now turns into a squared plus 13a plus 36. So now this is definitely factorable. We get a plus 9 times a plus 4. Once it's factored, substitute your x squared back in, x squared plus 9, x squared plus 4. Now these are not difference of squares, they are sums. But if we come over here to the side, I can solve it out to find what my zeros are and my factors are. So subtract 9 from both sides and take the square root. I get x equals positive negative 3i. So my x squared plus 9 is going to split into x plus 3i, x minus 3i. We can do the same thing with my x squared plus 4. Solve it. Take the square root. And I get positive negative 2i. So my x squared plus 4 can be split into factors of x plus 2i and x minus 2i. So that is the product of linear factors right here. These are all the linear factors of this polynomial all multiplied together. If I were to multiply this all back out, I would end up with x to the 4th plus 13x squared plus 36. And you'll notice I have 4 linear factors. My polynomial was a degree of 4, so I know that I've gone as far as I can. Don't forget, the problem also asks you to find the zeros, so you need to make sure that you list the zeros. So my x-intercepts or my zeros are positive negative 3i and positive negative 2i. Okay, let's do another one. So I have x to the 4th plus 3x cubed minus 19x squared plus 27x minus 252. So here we can't use substitution because we have way too many terms. We also can't use factor by grouping because we have way too many terms. So we're going to have to do our P's and Q's and figure out which factor will go into it. So my P's are all going to be factors of 252, and my Q's are factor of 1. Okay, and without having to write it all out, we can just say, okay, we know since Q is a factor of 1, we're just looking at our factors of 252. So start just by listing a couple. You know that 1 and you know that 2 are going to go into it. So we can start with those first. Okay. You also know that 4 is going to go into it. Keep finding just don't list them all out. Just list out a few, test those. If those don't work, find a few more, test those. If those don't work, find a few more, keep going. So you don't have to list out all the factors of 252 to start. Okay. I will go ahead and tell you that 4 is going to be a 0 of this. So we're going to put 4 into a synthetic division. And of course, we come out with a remainder of 0. So we have f of x over here. I'm going to go ahead and start writing out my answer so I can keep track. So I found out x minus 4 is a factor when I used the remainder theorem to plug that in. And when I divided by that, I got x cubed plus 7x squared plus 9x plus 63. All right, we're going to take a look at that third degree polynomial that we now have, our quotient, and see if it's factorable by grouping. So if you look at it, okay, the first term, the greatest common factor of the first terms will be x, and 9 in the second group, and I think I'm going to be able to factor by grouping here. So I'm going to go down here. And I'm going to factor this out by using factoring by grouping. So I take out an x squared, left with x plus 7, take out a 9, I'm left with x plus 7. So x plus 7 times x squared plus 9. So this polynomial here, this x cubed plus 7x squared plus 9x plus 63, that will factor to x minus 7 times x squared plus 9. Now remember, we have a fourth degree polynomial that we started with, so I'll need to have 4 linear factors. Right now I only have 3. So since, hold on one second. Okay, so since I have x squared plus 9 here, that's not a linear factor, that's a quadratic. So I can split that one up a little bit farther. And I'm going to do just what we did in the last problem. I know I'm going to need to subtract the 9 to the other side and take the square root, which is going to give me a positive 3i and a negative 3i. So there are my 4 linear factors. And then I need to just list what my zeros are. So my zeros will be 4, 7, and positive negative 3i. 4 zeros, 4 linear factors. Okay, we're going to do just one more together. Again, finding the complex zeros. So in that case, since we're finding all possible zeros, I have a fourth degree polynomial again, so I need 4 linear factors and 4 zeros. Not factorable by grouping, so you'll need to do your p's and q's. P are the factors of 40. And q's are the factors of 3. So when you do your p divided by q, take all of your p's, divide them by all of your q's. So you'll have all of your list of p's, and in addition, I'll have 1/3 2/3, 4/3, 5/3, and so on. But you know, since you only need one, go ahead and, like I said, you don't have to list out the whole list of P over Q. If you list out a few and then test those, if you can't find any of those, then list some more, so on and so forth. So you don't spend all your time listing out the P's and Q's. So I'll tell you that 4 is going to be a factor, or a 0 again, so f of 4. So we'll do some synthetic division using 4. Okay, and of course we get a remainder of 0. So over here to the side, listing out my answer as I go. So I found out using my P's and Q's that x minus 4 is a factor, and that would be multiplied by 3x cubed plus 14x squared plus 23x plus 10. So now I want to factor that new the quotient, the 3x cubed plus 14x squared plus 23x plus 10. Taking a look at it and some of the greatest common factors I would take out from each group, it looks like it's not going to be factorable by grouping. So what I'm going to do is keep testing other zeros that I have in my list. So I'll tell you that just to save a little bit of time, because I all know that you know how to test the zeros. Negative 2/3 is going to be another 0. So I'm going to come over here and put in my negative 2/3 into my synthetic division. Record my answer. X minus 4 stays, and now this big long polynomial breaks up into 3x plus 2. That's where that comes from, my negative 2/3, 0 there, times, and then over here I got 3x squared plus 12x plus 15. Okay, great. So looking at my new quotient, the 3x squared plus 12x plus 15. First thing you notice about it. You can take out a 3 as a greatest common factor. So I'm going to take out that 3 and put it out in the front there. And I'm left with x squared plus 4x plus 5. So double check, is x squared plus 4x plus 5, is that factorable? It is not factorable, so we're going to need to complete the square. So I'm actually going to come down here and complete the square. So x squared plus 4x plus blank equals negative 5. 4 divided by 2 squared is 4, so I add 4 to both sides. I get x plus 2 squared equals negative 1. Take the square root of both sides, and I get x plus 2 equals positive negative I. The square root of negative 1 is I. And then I need to subtract my 2 to both sides, so I get x equals negative 2 plus or minus I. So that means I can split up my x squared plus 4x plus 5 into x plus 2 plus I and x plus 2 minus I. So can I go any farther with that? I have 1, 2, 3, 4 linear factors, and my polynomial was a 4th degree polynomial, so that means I'm done. I have as many linear factors as the degree of the polynomial. And our zeros are 4, negative 2/3, and and negative 2 plus or minus I. 4 zeros, 4 linear factors for a 4th degree polynomial. All right. So I want you guys to practice these before you come to class. You just need to do 2 problems and make sure you check your answers in the back of the book. So you're in your calc book, page 237, number 31 and 33. Again, please make sure you check your answers before you come to class. So either you know if you did it right or you know if you have questions to ask when you get to class.